Hello Biology 100 students, welcome back to your lecture on the chemistry of life, atoms and molecules. This lecture has 5 different topics. We're going to talk about elements to start out with. We'll show you the periodic table. We're going to go through and talk about atoms and subatomic particles. We're also going to talk about ionic bonding and covalent bonding, and we'll wrap up this lecture with a discussion of the pH scale. Okay, so you've heard of elements before, right? Gold is an element, carbon's an element. So the definition is that an element is a pure substance that cannot be broken down into simpler substances by ordinary chemical means. And you probably already know that there's this table called the periodic table that has all the 112 known elements up there, and each of these elements is abbreviated by a 1 to 2 to 3 letter symbol. For example, O means oxygen, C means carbon. Now, you don't need to know all 112 elements here, but you do need to know how to identify, let's say, these top 5 right here. Oxygen, which is abbreviated as O, is really important in the human body, right? It makes up about 65% of the human body by weight because it's in water, and the body is made up of lots and lots of water. Okay, so carbon, abbreviated here as C, is also very important. Carbon is sort of the base atom or base element on which all the other atoms will combine to make up complex living organisms. So we are carbon-based. So about 18% of the body is made up of carbon. Hydrogen, also important. Why is it important? Well, it's part of water, and right, the body's made up of a lot of water, but it's also found in proteins and carbohydrates. And finally, nitrogen down here is still important at 4% of the human body weight, and it's principally important for being in nucleic acids, but also being in amino acids and proteins. And finally, calcium, you would think, would have a greater abundance by weight, but it's only 2% of the weight of the human body, but still very important. Calcium is necessary for bones. It's also necessary for blood clotting and a lot of things like that. So these are the top 5 elements you need to be able to know and recognize by their symbols for an exam. Now, you've heard it said before that life on Earth is carbon-based, but what does that mean? Well, what it means is that all the complex molecules in the body, whether they're carbohydrates, proteins, amino acids, lipids, etc., all of these molecules are based on the carbon atom. So we have carbon in everything. So imagine getting a chicken right here, this nice raw chicken. We take it from the grocery store, we put it in the oven, 400 degrees, it's been in for about 45 minutes, it looks good, and let's say we throw it up to, 500 degrees, or we turn it on broil, leave it in there for 3 hours. What is it going to look like at the end? It's going to look like a charred mess. So what is being left over there, what that char is actually the carbon that is left over in the chicken once we've used that heat to break down all these chemical bonds, release oxygen, release other gases as well. And what's left behind is this charred piece of chicken, which shows its sort of carbon skeleton that was making up that chicken to begin with. So just remember that life on Earth is based on carbon. Okay, so other major elements that we find in living things. We find phosphorus, abbreviated as P. We find potassium. We find sulfur. Sodium is really important, as are chlorides, all right? These are electrolytes, things that ionize in water and can generate electrical charges. We have magnesium down here as well. So all of these things are important in smaller amounts. And then we have some very important trace elements. That means they're only important in teeny tiny amounts. And in fact, if we have too much of them, they can cause problems. One of these I want to point out, of course, is iron. And why do we need iron in the body? Well, we need it for hemoglobin, which is that pigment we find in our blood that binds to oxygen. Okay, so let's look at a simple element here. And the element is sodium. And you're like, well, I've seen sodium before. I've got some in my cabinet. Well, no, that's not entirely true. What you have in your cabinet is this stuff right here, which is sodium chloride. You put it on your food, it makes it taste better. But if we go to look at elemental sodium, which is right here, it's actually a ductile, sort of cuttable metal that if you add it to water, it will blow up. If you ask your parents about this or your grandparents, they'll probably wax poetic about sneaking into the chemistry lab to grab a chunk of sodium, pulling it from the oil and flush it down the toilet to have this big explosion. Don't do that, by the way. The fact of the matter is that sodium is an explosive, poisonous metal, but when we combine it with chlorine, which is a corrosive, poisonous gas, we make something like table salt, which you can put on your food. So the moral of the story is individual elements have different properties than the compounds they might appear in. So sodium's bad, chlorine's bad, we add them together, and then we get something like sodium chloride, which you can add to your food. Okay, so elements versus atoms. An element is the fundamental pure form of a substance that cannot be broken down into simpler forms by ordinary means. And an atom is the smallest unit of an element that still retains the physical and chemical properties of that element. Again, the example I gave last time is imagine taking a bar of gold and cutting it down into smaller pieces. You would still observe that those small pieces of gold are lustrous, they're shiny, they're malleable, they're ductile. Theoretically, until you get down to the atom should still have those properties, although we wouldn't be able to perceive them. But once I break open that atom, as I can do with like a particle accelerator, it ceases to be gold anymore. Okay, so let's take a look at a very simple representation of an atom. So here we have an atom that has a nucleus, which has our protons and our neutrons, and outside the nucleus we have these electron shells where we have these negatively charged electrons. Okay, so the nucleus, first of all, contains the protons, which are the positively charged ions right here, and it also contains neutrons, which are neutrally charged. They don't have a charge. And then, of course, the electrons are out here in the electron shell. Electrons have a -1 charge. So these are the important things you need to know about these three subatomic particles. One, neutrons have no charge, but they do have an atomic weight of 1. 2, protons have a +1 charge and also have a weight or mass of 1. And 3, electrons here have a -1 charge, and essentially they don't weigh anything. So we're going to give them a weight of 0. So the atomic number of an element tells us the number of protons that element has. The atomic mass, on the other hand, tells us the mass of the element, that is the protons plus the neutrons. Remember, electrons technically don't have mass. All right, so let's take a closer look at the periodic table here. So here we have the periodic table for, or periodic symbol for carbon. So carbon has 6 up here. This is the atomic number, and it has 12 point something down here. So the atomic number tells us the number of protons. Okay, so if we know that it has 6 there, it tells us we have 6 protons. It also tells us, in most cases, the number of electrons, because for most atoms, the number of protons and the number of electrons are the same. Down here, we see the atomic mass, which is 12.011. This tells us the mass of the atom, and remember, the atom is made up of protons, electrons, and neutrons, but only protons and neutrons have weight. So we know that together, the protons and neutrons weigh about 12. So to figure out the number of neutrons, I take the atomic mass and subtract out the atomic number. Remember, the atomic number up here was the number of protons. So 12 minus 6 gives us 6. There are 6 neutrons in that atom. And you can always round this number. We'll talk about why this isn't a whole number in a little bit. Okay, now let's talk about isotopes. An isotope is an atom that differs in the number of neutrons with other atoms of the same element. So for example, if you look here all the way at the very end, we have something called carbon-12. This is normal carbon. Carbon has an atomic number of 6 up there, and it has an atomic mass of 12, and if you subtract 6 from 12, you find that carbon-12 has 6 neutrons. But let's look at carbon-13. If you subtract 6 from 13, you'll see that this one has 7 neutrons, so 1 extra neutron. And finally, carbon-14 has a mass of 14. We subtract out 6, and we find out that it has 2 extra neutrons. So an isotope is just an atom of an element that differs with the rest by the number of neutrons. Okay, now we're getting into something pretty important because we need to talk about the electron shells. The electrons are important in the atom because they determine whether or not an atom of an element will bind with atoms of other elements. Okay, so you do need to know that electrons occupy shells outside the nucleus. If you have a chemistry teacher, they'll probably look at you and tell you, well, this is very simplistic, we don't believe this anymore. For all intents and purposes, for a Biology 100 class, this type of representation is okay. So the maximum capacity of the shells differs depending on which shell it is. The first shell has a capacity of 2. All other shells that we're concerned with, we're going to say have a capacity of 8. Okay, so what you need to know is that atoms are most stable and most happy when their outer electron shell, their valence shell, is full. Again, this is a very important statement. Atoms are most happy or stable when their outermost electron shell is completely filled with electrons. Atoms want to be happy. Okay, now we're going to take a look at representations of 3 different atoms, and we're going to figure out together which one of these are stable or happy. So first of all, let's go to this one right here. This is a good old hydrogen atom. Hydrogen just has 1 electron in 1 shell. So if you remember what I said previously, the first shell can hold up to 2 electrons. Well, in this case, hydrogen only has 1 electron in there, so this shell is not full, and hydrogen ain't happy. Let's look at number 2. This is helium. Helium looks like hydrogen, except it has 2 protons and 2 electrons. So that first shell has all 2 electrons, and that shell is full. Helium is now happy. And if we look finally at carbon, we say that carbon has 6 electrons. Remember, the first shell can hold how many? That's right, it can hold 2, so 2 electrons, and the second shell is going to hold the remaining 4 in there. So the second shell could hold up to 8, but it only has 4. So carbon is not happy, neither is hydrogen. The only one that is happy here is helium because it has 2 electrons in its first shell. And because it's happy, it's stable. And what this means is that helium does not readily form compounds with other elements or other atoms. It's what we call a noble gas. It's very snooty, and it is not associated with other types of elements or compounds. That's why it's very hard to get it to form compounds with other elements. Okay, so atoms want to achieve a full outer electron shell to become stable. How can we do that? Well, there's 2 different methods. We can share electrons, as in covalent bonding, or we could donate or receive electrons, as in ionic bonding. Either way, we're going to get the formation of chemical bonds, which will link 2 atoms together. Okay, we need to go through some terminology before we talk about chemical bonding. First of all, we need to go back and talk about what a molecule was. A molecule was 2 or more atoms held together by chemical bonds. So you can see O2 means we have 2 oxygen atoms joined together. N2 means we have 2 nitrogen atoms joined together. And then we have something like CO2, which is a carbon and 2 oxygens joined together by chemical bonds. So all of these are molecules. Now, a compound is a certain type of molecule. A molecule, we said before, can be like 2 oxygens bound to each other. On the other hand, a compound is 2 or more atoms of different elements joined together by chemical bonds. So CO2 is a compound, sodium chloride right here, that's a compound, as is methane, as is glucose. Okay, if you remember what we said before, atoms want to be happy, and the way that atoms become happy is having a full valence shell or outer electron shell. Remember that first shell can hold 2 electrons, but the subsequent shells can hold usually 8 electrons. So we want to become happy by getting a full outer shell. How do we do that? Well, the first method here is electron sharing, something called covalent bonding. Covalent bonding is a chemical bond created when atoms fill their outer electron shells by sharing electrons with other atoms. So let's look at an example of covalent bonding. The example we have here, we have 2 atoms of hydrogen and 1 atom of oxygen. Let's look first at our hydrogen atoms. Now the atomic number for hydrogen is 1, which means it has 1 proton and 1 electron. So remember that the first electron shell can hold up to 2, so this hydrogen isn't happy. It still wants 1 more electron. The same could be said with a hydrogen on this side too. Atomic number of 1, it has 1 electron, but it could use 2 in order to be happy or stable. Now let's take a look at oxygen. Oxygen has the atomic number of 8, and that means it has 8 electrons and 8 protons. Now, let's take a look at oxygen here. The first two electrons go in the first shell, so that's 2 electrons, and it leaves 6 remaining for the second shell. Now remember that second shell can hold up to 8, so it's deficient 2 electrons. It needs 2 more electrons in order to be happy. Can you see what might happen here? So now what you can see is we formed a very stable molecule, a water molecule, by combining oxygen with hydrogen. Now oxygen needed 2 electrons, but now that it has the 2 hydrogens in there, it looks like it has 8 electrons in the outer shell, so its shell is full. You might be saying, well, what about hydrogen? It still looks like it only has 1. The thing about these electron shells, the electrons are spinning around from one atom to the next very, very quickly. So sometimes it's around oxygen, sometimes it's around hydrogen. In either case, it's making hydrogen a lot more stable and a lot more happy because it now feels like it has 2 electrons in the outer shell. Okay, here's another example of covalent bonding. If you take a look at carbon, remember it had an atomic number of 6. That means it has 6 protons and probably 6 electrons. So remember how many electrons fit in the first shell? 2. That leaves how many left over for the second shell? 4. How many can that second shell actually hold? Well, it can hold 4, so it needs 4 more to be happy. And here we have 4 hydrogens. Each hydrogen has 1 electron and needs 1 more electron to be happy. So what's going to happen here? Bam, you got it. We just formed a covalent bond between the 4 hydrogens and the carbon in order to make this great gas known as methane. So there's many different examples of organic molecules that are created through covalent bonding. We showed you methane already. There's something called ethane as well, and then something called ethylene. Now the thing I want to show you right here is it's possible to share more than 1 pair of electrons between atoms. In this case, we form what we call a double bond, and as you can imagine, double bonds are stronger than single bonds. Okay, so aside from sharing electrons, there's also another way to become more stable, and that's to give up or receive electrons, and we call this ionic bonding. Ionic bonding is a chemical bond created when atoms fill their outer electron shells by either giving up an electron or receiving an electron. Okay, so before we talk about what ionic bonding is, we need to talk about what an ion is. It's not just a cheap car. An ion in this case is an atom that has gained or lost electrons and has a net positive or negative charge. For example, if you see Na with a plus next to it, that means we have a sodium cation. The only way that sodium gets to be positive is by giving up an electron. On the other hand, we see chloride down here. We can see that chloride here is negative because it has taken on an extra electron. So by either giving up or receiving electrons, we can become positively or negatively charged. Okay, now let's give an example of how ionic bonding works. Starting out on this side, we have the atom of sodium. Sodium here has an atomic number of 11, and that means it has 11 electrons and 11 protons. So let's look at the first shell. Remember that first shell can hold 2, and it's full with 2. Second shell can hold 8, and that's full with 8. So that's 8 plus 2 is 10, leaving only 1 electron left in the third shell. So sodium is definitely not happy. It would need to either get an additional 7 electrons or give away an electron in order to be happy. Now let's go look at chlorine. Chlorine has an atomic number of 17. So remember, 2 electrons go in the first shell. Okay, that leaves us 8 in the second shell, so that's 10, and that puts 7 in the third shell. And so it only needs 1 more electron in order to be happy. Can you see what can happen here? Sodium wants to give away electrons. Chlorine wants to take an electron in order to be happy, and that's exactly what happens with ionic bonding. Essentially, sodium gives away an electron, and in doing so, we can think of that third or valence shell as disappearing so that the next internal shell will be full, and then chlorine gains an electron to become chloride, and then it has 8 electrons in its outer shell, and it is happy as well. So now what we have are 2 different ions, and we call them ions because they are charged. Remember, sodium originally had 11 protons and 11 electrons. Well, in giving up an electron, it now has 11 protons and 10 electrons. So it has a positive 1 charge. It's a cation. Now let's look at chlorine. This is actually now called chloride. So originally, I think we had 17 electrons, right? And we got an extra electron from our sodium. So now we have 18 electrons and 17 protons. So we have 1 more negative than we do a positive. So we are now a negatively charged or anion. So we have a negatively charged ion and a positively charged ion. And what do we know about opposites? That's right, opposites attract. So these ions will stick together by these ionic charges. Okay, here's some different examples of ions that are important in biology. Hydrogen ions, which we see up here, H+, are what we find in acids. So acids are things that give off protons or hydrogen ions. We have calcium ions. This is a positively charged ion of calcium. And we have positively charged up here of magnesium. Now, when you see positive, just realize that the reason it's positive is because it gave away an electron. If you see a positive 2 or a positive 3, that means it gave away 2 or 3 electrons. And if you see something like this, which is negative, that means it's an anion, and it got that way by accepting an additional electron. Okay, now that we've talked about bonding, we're going to spend the last part of the lecture talking about some unique properties of water. Why do we care? Well, water makes up a lot of the weight of living organisms. We know that water is essential for life, but water also has some unique properties. First of all, it has a high heat capacity, and what that means is it takes a lot of heat to raise the temperature of a small vessel of water even 1 degree Celsius. Secondly, water has a high heat of vaporization, and that means it takes a lot of heat energy to cause that water to go from a liquid water to gaseous water. And thirdly, water is polar. It has these sort of negative and positive ends to the molecule. Okay, remember that water was formed through the covalent bonding of one oxygen atom with two hydrogen atoms. And remember that covalent bonding was the sharing of electrons. And this theoretically is great because it allows oxygen to achieve a full outer shell of 8 electrons and hydrogen to achieve a full outer shell of 2 electrons. But think about the last time you shared something with your boyfriend, girlfriend, spouse, or brother or sister. Was the sharing always equal? Probably not. My wife and I, for example, shared a car when we first got married. And did we get it equally? No, she got the car a lot more often than I did. And that's the way it happens with oxygen. Oxygen, even though it's sharing electrons, is very greedy with those electrons. So they tend to spend a lot more time around oxygen than they do around hydrogen. And because they spend less time around hydrogen, what's left over at hydrogen here is just a proton in the nucleus. And so it gives this hydrogen end of the molecule a partial positive charge right here. On the other hand, the electrons, which are negative, spend more time around oxygen, which give the oxygen side of the molecule a slightly negative charge. So we have partial negative and partial positive charges. And what do we know about opposites? They attract. So because we have polarity in the molecule, the hydrogens are partially positive and the oxygens are partially negative, water molecules line up with each other in a certain way. Think about how dogs line up, right? Do they line up nose to nose? No, it's nose to butt. And so the nose here would be like the oxygen side and the butt would be the hydrogen side. So we form these temporary associations between adjacent water molecules called hydrogen bonds. Now I should point out, these aren't chemical bonds. They're not strong. They're not going to hold these molecules together. And all I need to do to break them is just run my hand through them. In fact, hydrogen bonds are being formed and broken thousands of times per second in any vessel of water. We can also form hydrogen bonds between other things that have polarity as well. So here we have a water molecule that's forming hydrogen bonds with ammonia right here. Okay, so just a final review of the different types of chemical bonds. We said that covalent bonding occurs when atoms share electrons in order to achieve a full outer electron shell. Ionic bonding occurs when atoms either give up or receive electrons to achieve that full shell. And hydrogen bonding is a temporary association between molecules in which their atoms are sharing electrons unequally. And so we see this happening with water molecules where oxygen is more greedy, it hangs on to the electrons more often, and so it gives the oxygen end of the molecule a negative charge, partial negative charge, and the hydrogen end a partial positive charge. And that allows these molecules to stick together in a certain way. Okay, we're going to shift gears now and talk about acids and bases. Now, an acid is anything that gives off hydrogen ions in a solution. Oftentimes you'll see the terminology that it's a proton donor. And what I want you to think about here is, what is a hydrogen atom? Well, a hydrogen atom has one proton and one electron. If that hydrogen atom gives up an electron, essentially it's just a proton. So anything that gives off hydrogen ions is going to be called an acid. So here we have hydrochloric acid, right? So HCl, which we find in the stomach, add it to water, it dissociates into hydrogen ions, which are positively charged, and chloride ions, which are negatively charged. So that forms an acid because it gives off hydrogen ions. Now bases, on the other hand, do the opposite of acids. They scavenge up hydrogen ions or protons from a solution. For example, if I have sodium hydroxide and I add it to a solution where there's an acid, the hydroxyl ions in there are going to scavenge up any remaining hydrogen ions and form water. So this is a process called neutralization. So when I take, for example, hydrochloric acid up there plus sodium hydroxide, the hydrogen ions are going to bind with the hydroxyl ions to make H2O, water, and the rest will form the salt sodium chloride. So neutralization neutralizes the acid. A buffer is anything that can help reduce dramatic changes in pH of a solution. For example, bicarbonate is a buffer that we have inside of our bloodstream that helps prevent any major shifts in pH of the blood. Okay, we're going to wrap up this lecture by talking a little bit about the pH scale. Now, the pH scale is used to measure the relative alkalinity or acidity of a solution. The pH scale goes from 0 to 14, and dead in the center here we have a pH of 7, and 7 is what we call neutral. So 7 is the pH of distilled water, which is very safe. We can drink it, we can put it on our hands, etc. Now, as we go down the scale, that direction, we are going to decrease the number but increase the acidity. So for example, coffee has a pH of 5. It's a lot more acidic than water is, but how much more acidic? Well, each jump from 7 to 6 is an order of magnitude or a 10 times increase in the concentration of hydrogen ions. So we have two jumps, 10 and 10. And you might say, well, coffee is 20 times more acidic than distilled water, but you'd be wrong because this is a log scale and we don't add the 10 and the 10, we multiply it. So in truth, it's 10 times 10. That is, coffee is times more acidic than distilled water. Okay, now let's look at lemon juice. Lemon juice has a pH of around 2. So let's look at how many jumps that was. So 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps. So again, it's 10 times 10, which is 100, times 10, which is 1,000, times 10 is 10,000, times 10 is 100,000. So that's a big change in acidity between a 7 and a 2. Okay, we're not even going to worry about stomach acid right now. Suffice it to say it's a lot more acidic and there's more math to do. The big concept here is that there's a 10x change in the concentration of hydrogen ions as we go down the scale. It becomes more abundant when we go from 7 down to 0. On the other hand, hydrogen ions become least abundant or less abundant as we go up the pH scale. As we go from 7, let's say, to what we have right here, 9, okay, that's going to be a 100 times reduction in the concentration of hydrogen ions. Okay? And as we go up the scale, we can have things that are more alkaline, Phillips Milka magnesia, and then finally, easy off oven cleaner. Now, one thing I want to talk about acidity and alkalinity is that people think because something is corrosive that is acidic. And that can be true, right? If you look at things at the very end of the pH scale down by the 2s that are acidic, like stomach acid and lemon juice and stuff like that, they definitely are corrosive. But the same can be said for things that are at this end of the pH scale as well, right? Easy off oven cleaner has a pH of around 13 or so. You wouldn't want to get it on your skin because it is very corrosive. So things towards the middle of the pH scale usually tend to be less corrosive. Things towards the ends tend to be more corrosive. And remember, things that are below 7 are acidic, and things that are above 7 are basic. Okay, you've reached the end of Lecture 5 on chemistry, molecules, and compounds. Now, I know that was a very intense lecture. If you don't understand all the material, make sure you go back and review the parts of the lecture that you're having problems with. And if you still have questions, give me a call or drop me an email. Thanks.